partial fractions. In junior school, we do a heck of a lot of work on algebraic fractions where we're adding fractions together to create one single fraction. We don't tend to do a lot going back the other way, and that's really what partial fractions is. It's getting a single fraction and then breaking it up into the sum of several fractions, so going back the other way. And that's very useful in integration. So let's look at this idea of partial fractions. So it's when we have a fraction situation, and first of all though, we look at the degree of the numerator and the degree of the denominator. If the degree of the numerator is bigger than or equal to the denominator, do a polynomial division first. So get that out of the way. Then, once we've got that degree, then we factorise the denominator. Now, once we've got it factorised, we can set up our partial fractions. So if we have a linear factor, then I just write it as a constant on top of that linear factor. And I set up a fraction for each one of those. If I have multiple ones, so like x to the minus a to some power, then I write one fraction for each of the powers. And then the only other possibility we would have is quadratic. Because remember, all polynomials can be factorised down to be a combination of quadratic and linear factors. And so if it's a quadratic, then on the top of the fraction, I want a linear function. So I write ax plus b. All right, so let's start with this one. Very simple one to start off with. Just to highlight, first thing we look at is the degree. And the degree of the top is a quadratic, bottom's linear. So we do a polynomial division. You may be able to do it by sight, but just in case. Okay, let's do our division. X and x squared. Oh, that's x. And minus x, minus 1. And a remainder of 1. So we know we can rewrite that one as x minus 1 plus 1 on x plus 1. They're all things we can handle with integration, and so we get our answer straight away. 3 on x squared minus x. So no division to be done. Factorise the denominator. We get x outside of x minus 1. So I've got two linear factors. So I set up a fraction for each of those linear factors. A on x plus b on x minus 1 is equal to 3 on x minus 1. If I get rid of the denominators, so multiply everything by x minus 1, I come up with this equation which will allow me to find a and b. And by sensible substitution, we can pick those values out. By sensible substitution, something like this. Well, I'm going to pick x equals 0 because that'll make the b disappear and I can get a straight away. So a is negative 3. So the next logical one to substitute in then is x equals 1 because it'll get rid of the a and now I can work out b. So one's negative 3, one's positive 3. I can now rewrite my single fraction as the sum of two fractions. And both of those, well, we're always going to end up with a log function if you think about it. Because we're saying a linear factor with a constant on top. So it's always going to be a log situation. So minus 3 log x plus 3 log x minus 1. Because the coefficients are both 3, I'll combine that into 1 log. So that's reasonably simple to do. So 3 log x minus 1 on the x for that one. All right, x plus 5, x squared minus 3x minus 10. Factorise, we get x minus 5, x plus 2. So same idea, let's set up a fraction for each of those. Get rid of the denominators. Again, sensible substitution. Start off with negative 2, that'll get rid of the a. We'll get b as minus 3/7. Now I'll go with x equals 5, a is 10/7. So I now can rewrite both of those fractions. So what we got, well, again, as I was saying, got to be a log situation. So I've got 10/7 minus 3/7. In this case, I didn't bother combining them because the coefficients are different. I suppose I could have brought the 10 into the first one, the 3 into the second one, then the coefficients both are 7th on both of them, but no, I'm not going to worry about that. X cubed plus x. So factorise that one. I've got a quadratic and a linear. So the quadratic, we create a linear function on top. All right, sensible substitution. Let's pick, 0. 0 will get rid of both the b and the c. So I get a is equal to 1. There's nothing stopping me using complex numbers because I will get rid of the a straight away. If I substitute in I get minus b plus ci equals 1, and I just equate the real part and the imaginary part. So b is negative 1, c is 0. And there's our fractions. So again, the linear one, yes, it's log. And in this case, the second one turns out to be a log as well, because I've got linear on quadratic. So we've got log x minus a half log x squared plus 1. You'll notice I didn't bother with the absolute value on the second one because I know x squared plus 1 is always going to be positive. I mean, it's not wrong to still have the absolute value there. This one's already factorised for us, but you'll notice we have a repeated linear root here. So this is the one where I'll set up a fraction for each of those powers. So I've got an a on x plus 1, a b on x plus 1 squared, and then on the quadratic cx plus d. Get rid of the denominators and sensible substitution. What's the first one I'm going to do? -1, that'll get rid of the a. Oh, it gets rid of the cx plus d as well, doesn't it? Yeah. So b is -1/2. If I substitute in I, that'll get rid of the x squared plus 1s. And so I've got -2c plus 2di is I. So c is 0, d is 1/2. Now I'm probably just going to pick something really simple like 0, because I know what b, c and d are. So if I sub in 0, I just have an equation. 2a plus b plus d is 0. I know what b and d are, so I can work out a, and it turns out a is 0 anyway. We end up with two fractions. The first one, it's still a linear, but that's not going to be log because it's now x plus 1 squared. The second one, x squared plus 1, will give us a inverse tan function. So we'll end up with a half of 1 on x plus 1 plus the inverse tan of x. Setting up those simultaneous equations, terrific, works every time. Can sometimes be time consuming to find something that's very quick to find. So here's another way. First of all, let's just say we've only got linear factors, so something like this. A on x minus a, b on x minus b, c on x minus c, and we'll keep going and we keep going. If I want to find a, then this is what's sometimes called the cover-up method. So I imagine covering up the x minus a. It's like it's not there. And if it's not there, then I'm saying my function becomes function x on x minus b, x minus c, however many linear factors I've got. And all I've got to do is substitute a, whatever that a is, x minus a, into it, and that'll work out a for me. So I just cover up the factor, substitute in a, get my answer. Then to work out b, cover up the x minus b, substitute in b, I get my answer. And so on and so on and so on for each factor. So back to the same examples we did before, just to illustrate how much quicker that is. All right, I want to find a. So I will cover up the x and substitute in 0. Oh, it's -3. Okay. Now I want to work out b. I will cover up the x minus 1 and substitute in 1. Oh, that's 3. Let's go through it with the second example. So to work out a, cover up the x minus 5, substitute in 5, you get 10 on 7. To work out b, cover up the x plus 2, sub in -2, we get -3/7. So any time you've got a linear factor, it's very, very quick. Now, most people just show that for the cover-up method. But of course it can still work for quadratics as well. You just have to use complex numbers. Right? So here's the next one we had. A on x, bx plus c on x squared plus 1. I want to work out the a, cover up the x, substitute in 0, and we get 1. I want to work out the bx plus c, cover up the x squared plus 1, and substitute in I. So you get bi plus c is 1 on I, and the reciprocal of I is minus I. So b is -1, c is 0. Let's look at the next one. Okay. We want to work out the a. Well, that's okay. It's a linear one. Cover up the x minus 1, substitute in 1, and we get 1. Oh boy, now the fun bit. We want to work out the bx plus c. Cover up the 4x squared plus 1, but we're going to have to substitute in I on 2. So bi on 2 plus c is I on 2 squared plus 4i on 2 over I on 2 minus 1. Oh well, a little bit of work to do, but there it is. So the reality of the situation is it's good to know both ways, Because for the simple ones, bang, cover it up, you got your answer. But for something like this, I'm probably not going to use the cover-up method, because there's a lot of working out there. Now, what about the multiple factors then? That's the case I haven't considered yet. Can still use it. Watch out. Because, I've got x minus 1 and x minus 1 squared. If I cover up the x minus, which one am I going to find, the b or the c? Well, let's do the a. That's easy, because there's only one x plus 2 there. Cover up the x plus 2, substitute in negative 2, we get negative 2. It's the constant of the higher power we find using this method. So it'll be the c that we'll find. Why is it that one? Because I'm covering up the x minus 1 squared. So it's c that I end up finding. So substitute in 1, I get c equals 3. How do I get b? I just do a simple substitution like x equals 0 or something like that. So if I let x equal 0, we end up with minus 1 minus b plus 3 is 0. So b is 2. B is 2. Look, it's about having a suite of techniques. You know, like, all right, I'll try it this way. Oh, this way is a bit of a hassle. I'll do it another way. So having multiple ways of approaching problems is going to help us. Ooh, so okay, let's have a go at this one. The x plus 1 squared is going to find me the b, because that's the highest power. So I get b is minus a half. The x squared plus 1 I can cover up and substitute in I. So that'll get me the c and the d. All that's left to find now is the a. So I'll just do a substitution. And I'm usually always going to pick 0 because it's so easy to substitute in. Unless, of course, I've already used it. And so we get a plus b plus d is 0. But we know b and d, so that works out that a is 0. Now, what happens if you've got a quadratic denominator that can't be factorised? So say it ended up like this. Well, the a, that's nice and easy. What do I do for the second one? Complete the square. As I say, you might not actually do this, but theoretically you can still do it. Complete the square to find the appropriate substitution. So x squared plus 4x plus 5 would be x plus 2 all squared plus 1. So I'll let x equal negative 2 plus I. So b times minus 2 plus I plus c will be 2 on minus 2 plus I plus 1. A little bit of calculation, but eventually we get it. There's b is minus 1. And then from that we can work out c is minus 3.
You write that and I'll be fine. You write that and I'll be fine. You write that and I'll be fine.